Okay, this orange vector now I'm going to call the vector v, and if my I, j, and k vectors are in the directions of these sides, these edges of the rectangular solid here, you see that you're going to go A in the j direction, negative b in the I direction to get from here to here, and c in the k direction, so that the vector is negative bi plus aj plus ck. Now v can be represented in any of a number of ways. It can be represented, we could represent it as an order triple negative BAC. We could represent it as negative BI plus AJ plus CK. We could represent it in bracket form with negative BAC separated by commas, making this a row vector. We could write it without commas as a row. We can write it with semicolons, making it a column vector. Or we can put it in columns. Any of these can be used to represent the vector v. Now, v dot v, as we should know, is just then and I'm going to write without commas. We make a row vector out of v, and then we make a column vector out of v, and we multiply the row by the column, and very clearly we get v squared plus a squared plus c squared, which, except for the order of terms, which doesn't matter, is identical to the square of this distance. So we define length of v by definition, well, it's not quite by definition yet. We denote that by the length of v, absolute value signs with an attitude, and that's just the square root of v dot v. Because of course v dot v is a squared plus b squared plus c squared. The square root of that then would be the square root of a squared plus b squared plus c squared, corresponding to the length of that vector. So there's definition of length, and this definition generalizes to Rm. It doesn't matter how many dimensions your real Euclidean space has. This definition of length applies in any dimension.